Hello and welcome. Today we'll be talking about compounds in aqueous solutions and overall net ionic equations. So we're trying to figure out what happens to compounds when you put them into solutions. So let's talk about this. First of all, what happens to solids? And you have this in your sheet. If something does break apart, all right, we've talked about this before, but if a sodium chloride breaks apart, as a solid, it's going to break apart into sodium ion and a chloride ion, one of each, and we have aqueous. It'll become aqueous. Let's say I have 1 mole of calcium or sodium chloride. If they break apart, it'll break apart into 1 mole because it's just splitting this apart and making one of each. I'll make 1 mole of sodium ions and 1 mole of chloride ions. That's what will be formed in the solution, those ions, as the solid breaks apart. Let's say we have a different type of situation where we have aluminum chloride breaking apart. Again, it is soluble in water, so it will break apart and it will dissolve, and I'll have an aqueous. Remember, it's going to break apart into 1 aluminum, but now I'm going to break into 3 chloride ions. So that's why I have 3 of them here. So now in this case, if I started with a mole of aluminum chloride, when I put it in the water, I would have 1 mole of aluminum ions and 3 moles of chloride ions for an overall 4 moles of ions. So I have more ions in this solution. I would expect, like if I was going to light the light bulb like we did back in chapter 6, I would expect this to light the light bulb brighter, or more to have more ions, because here, if I dissolve 1 mole of this, I only have 2 moles total. So for a total of 2 moles here, I have twice as many moles, so I'd expect it to be twice as bright. Now, another type of, or double displacement reaction is oftentimes called, or one type of that is called a precipitation reaction. And that's if you make a precipitate. We talked about this back in chapter 8. So what we're doing right now really is review of chapter 8, looking at 2 aqueous solutions that would get together, or that could get together and possibly form a precipitate. So this is the example we actually did back then in chapter 8. So I'm going to take lead 2 nitrate, which is aqueous, plus potassium iodide. And whenever we're talking about precipitation reaction, we're talking about 2 aqueous things, and then we are seeing if it forms a precipitate. One of the products does. Now I have lead 2 iodide, so lead's a +2, iodine's a -1, plus potassium nitrate. Now, at this point, it is time that we need to figure out if these things are aqueous or solids, and we need to go back to page 437. In this case, iodides aren't on page 47, but potassium and nitrates are, and it says that they are always soluble. The potassiums and nitrates are always soluble, so that means that they will be aqueous. I can tell you from doing this one, and I've done this demo, this is the demo where we start with 2 pretty clear liquids, and we made a really bright yellow precipitate. And that bright yellow precipitate is this lead 2 iodide. So that is a solid. Even though it's not on page 437, lead iodide is not soluble in water. So I know that's a solid. So that is my formula equation. I could then balance this by making sure all the atoms are balanced on each side. If I did that, it would look like this. So here's my balanced chemical equation. Again, this is stuff we did in chapter 8, just showing what it makes and how it makes a solid. Now it's where it gets different and new. And we talked about this, but we didn't really explain how it gets different with the net ionic. We kind of talked about how they split apart. So an overall ionic equation, what does that mean? Well, just like we did in the first slide, or the second slide, where we went and broke apart sodium chloride and aluminum chloride, that's what we're going to do here too. Because if this is an aqueous solution of lead nitrate, that means that there's just ions in the solution. Same thing with this. There's potassium and iodide ions in the solution. And then we just mix all those ions together and see what we get. So the overall equation in this case would be a lead ion 2 plus, because there's only one of them, and that's aqueous, plus 2 nitrates, there's 2 of them, NO3 minus, and that's aqueous, plus 2K plus, and that's aqueous, plus 2I minuses, and that's aqueous, yields, again, we're going to break these apart, 2K plus, and that's aqueous, plus 2 NO3 minuses, and those are aqueous, because these are, anything that's aqueous, we're going to break apart into its individual ions. But the solid here, this PbI2, stays solid, because it does not break apart in water. So it does not have free lead and iodide ions floating all over the place. All right? So that's called an overall ionic equation, where you show all the ions. Everything that's aqueous, these 3 items that are all aqueous, we broke apart into individual ions. And rather than showing them together, because they're not, if this is an aqueous solution, really these 2 things are not together. They are not together. They're broken apart if they're aqueous. Any ionic compound that's in water is broken into ions. So they're all broken apart. So why not show them broken apart? So that is what's really happening. Now a net ionic equation. A net ionic equation is an equation where you get rid of what we call the spectator ions. And the spectator ions are ions that show up on both sides and don't do anything. They're aqueous on both sides. So if I look here, it's nitrates, 2 nitrates, and here I have 2 nitrates. Here I have 2 potassiums, and here I have 2 potassiums. So those are called spectator ions. I can eliminate those from my net ionic equation, because they're not really doing anything. They're ions before, they're ions after. They're spectators. They're watching the action happen. So my final net ionic equation is lead 2 plus 2 iodide ions, which were aqueous. Now they have formed a solid lead 2 iodide. And that is what's called a net ionic equation. Those of you that are taking AP chemistry, this are the equations you have to write on the AP test. That's all that you can write. You can only write net ionic equations. So anything that breaks into ions, you need to show that. And we'll practice that a lot, but that is the equations part of the AP test. Lots and lots of net ionic equations. All right, so I would like you to try to solve this. So the steps, just like Chapter 8, you're going to have to figure out what the products could be. And I'm going to tell you in this case, it is silver, little technical error. This is silver chloride is one product, and sodium nitrate's the other product. So I want you to get the word equation. This is starting the word equation, so you finish it. I want you to come up with a formula equation. I want you to come up with the balanced chemical equation. I then want you to come up with the overall ionic equation. So breaking apart any ions or any aqueous substances on either side. And then the final thing would be the net ionic equation. So you're going to take the example like we did and the ones that are in the book and figure out what all these things would be if silver nitrate and sodium chloride got together. So go ahead and give that a try and bring that with you to class.